All right, so yeah, today we're talking about neural networks. Specifically, we're talking about perceptrons. So I want to throw this out there just kind of get you all thinking in the right direction while I'm okay, perfect. I want to throw this question out there at everybody while I wait painfully for TensorFlow to finish installing on my computer because I never installed it. What is a perceptron? Exactly. Like if you had to define a perceptron, how would you define it?
The most basic neural network there is.
Okay, that's one way. What's another way you could? How else would you define a perceptron?
Just an
Anybody?
input to an output, right?
Yeah, it's basically a function that kind of learns. So it takes inputs and gets outputs and learns from the outputs.
Okay. Okay. Yeah, I can kind of see that. You're on the right track, right? But as a summation of its parts, right? How would you define a perceptron?
What is this? Why does this sound like a trick? Is this a trick question or something? I don't know.
No, not at all. Not a trick question. I'm just buying time while I wait for TensorFlow to install.
Oh.
Yeah, pretty much what I'm doing right now. Not that it matters. I'm going to spend like 5 seconds on TensorFlow, but you know, that's how I roll. Okay. So you can think of a perceptron, right, as the values and the weights, a function of the inputs and the weights that connect them to get an output, right? And I'm going to do a large portion of this on a whiteboard because I feel like this has worked in the past, right? Kind of sort of explaining. You all know the basic diagram, right? With the circles and the lines coming off the circles, and they're all connected, and it just looks like a well, just looks like a bunch of circles with lines connecting them. It is really the best way to kind of visualize this, but I feel like it needs a little bit of explanation. So let's look at this. All right. This is a perceptron. You have an input node 1, my awesome circle, input node 2, and an output node. Okay? So who wants to tell me what a node is? What is a node? I've drawn a circle. What does it represent?
It represents the features of the database. Like every node, it's a column or like feature.
Okay. Okay. So on the input node, right? So this here, where is my thing?
Can you say it basically accepts a number and outputs a number?
Input. Okay. So this is the input layer, right? So here in this perceptron, I have 2 inputs, right? So each of these will contain a value, right? Let's give ourselves some example data to work with. Let's say I have x1, x2, and y. And inside of x1, I have 0. Inside of x2, I have 1. And y is something. Okay? So this is what I'm working with. Okay? If this is my data represented in the form of a data frame, this row will be going in first, right? So we're going to take this row of data, and we're going to take x1 here, okay? And it's going to go in the first node because the values will be entered in sequential order, starting with value 1 in the first node all the way to value n in the nth node, right? That's how this works. So 0 will go into this node. 1 for the next value will go into the next node here. Okay? Now we're going to connect it to this output node because if we didn't, this would be pointless, right? What does this line represent? Anybody know? What is this line?
The axon.
I heard an axon. Is that right? What the heck is an axon?
In the way it was explained biologically, it's an anatomy, the nerves.
Isn't it the weight?
It's the weight. Oh, you're thinking biologically. Okay.
Yeah.
Okay. No. That's not quite the same thing. It is a weight. Okay. It contains some value, typically starting from a random point. Okay. By convention, right? You have weight 1 and weight 2. Okay. Connecting input layer 1, or rather input node 1 and input node 2. Each have their own corresponding weight to the output node. Okay. What happens at the output node? What's going to happen here? We've got 0. It passes along this line, picking up or combining with weight 1 here. And 1 goes along this line, combining with weight 2. What happens at this node when they join together?
Modified.
Activation function.
The activation function. Okay. So here we calculate function of x, where x is what?
The value of one of the inputs.
I'm looking
Not
for
one of,
one term. One term. What is x? Remember, you have this
Well-
linear combination and this linear combination. They intersect here. What's going to happen?
Yes, no?
Hmm?
Oh, no, nothing. I was thinking it's bias, but there's,
The sum of all weights.
The weighted sum.
oh,
That's close enough.
X is the weighted sum. Okay, what is our function in the case of the example from today and yesterday? What activation function did we use? It's got a name.
Sigmoid.
The sigmoid. Right? If anyone doesn't know, the sigmoid, right, starts at 0, where 0 is here, and 1 is here, right? And it's just this function that sort of encapsulates everything in between 0 and 1, right? Looks something like that. Looks like a little S curve, all right? And all values, this here asymptotes to 1, and this, is infinitely approaching 0, right? All right, so you have this sort of, these values can exist anywhere along this line. When we run this through this function, right, we combine our weighted sums, we take the sigmoid of the weighted sum, right, as the activation. What is this output? And this is a little bit of a trick question. How do we, like when we talk about this output, it is the what?
Activation.
Not quite the activation. It is the activated output, but what is the activated output?
It's the derivative.
Not quite no, it's not the
No.
derivative.
Okay.
We're going to be doing that. That's part of back-propagation. What is the activated output?
The probability of it being 1.
The probability of a positive class, right? Think about it. Between all infinite number of values between 0. Oh, we're not doing this today, man. Calm down. It's the probability, right? Think about it. It takes some value between, like 0.1 at the bottom, down here, and 0.99. What does that look like? Looks like percentages, right? That's exactly what that looks like. This would be like 10%, and this would be like 99%. My dog is getting shocked by his bark collar. That's what's happening, in case you're wondering. I swear I'm not kicking him. All right, so he's supposed to stop, and that's supposed to stop him. Anyways, so these are percentages, right? This is, if the value is up here, then it's a very high percentage that it's positive class. And if it's down here, it's a very low percentage that's positive class. Okay, so this is our probability. Okay, so we get this probability in the form of our activated output. Okay, and so in this particular case, let's say for whatever reason these combine, and our probability this is just sort of an example, right? We don't know what y is. Let's say y is supposed to be a positive. It's supposed to be 1, right? But our probability is 0.3. Okay, so we combine this. We don't know what weight 1 and weight 2 are. It's kind of pointless. We don't really care. Okay, we can abstract that away for the time being. But we did a linear combination. We took the sigmoid of the weighted sums, and we got 0.3, a real tangible value, right? Roughly equating to 30% of it being positive class. Well, that's wrong, right? We would say that it really needs to be above 50% probability of being positive class in order for us to say that it got it right. Wouldn't you agree? Like, definitely needs to be above 50%, right, to be majority positive class prediction. Okay, so this is a majority negative class or a not positive class prediction. So we would say it got it wrong. How can we fix this? What would be the first step?
Adjust the weight.
Yeah, we're going to need to adjust the weights, right? So these values aren't wrong. How do we know we need to adjust the weights? Let's start there. Well, 0 is not wrong. It came from x1, and 1's not wrong. It came from x2. The only variables that we have are this weight 1 and weight 2, right? The sigmoid activation function is not wrong. It's just, it has a very simple job, right? So these are the only 2 things that can change. We need to change them. Now, how do we figure out how? How do we know by what they need to change? What can we do?
Calculate the error, right?
We're going to need to find the error. Okay, so we know this is supposed to be a 1, and we can say that, well, for it to be positive class, it would need to be 100%. And that's the same thing as saying that this needs to be 1, right? Or 100% positive class. And I'm making this distinction because it's very important. It's not predicting 1 or 2 or 3. It's predicting 100% positive or 0% positive, right? How much, what side of this, which extreme does it need to be? All right, and I'm saying I have a positive class, so it needs to be 100% positive class. And therefore, we can say that our error equals what? How do we define this error?
It's 1 minus 0.3.
You got it.
I mean, from correct output, like a minus, like error loss. Okay.
So we're going to say that it needs to be 1 minus 0.3, or another way of thinking about it is the equation, or the expression would be, it needs to be y minus the sigmoid of x, of the weighted sums, right?
Is it like the probability of failure?
What's that?
Is it like probability of failure?
We're saying failure?
Yep.
I don't think that that's right. No. This is. Are you talking about this probability here?
Mm-hmm.
That's the probability of y being positive class. So positive class would be 1, not positive class would be 0.
Okay.
Okay. And I'm saying it needs to be 1. It needs to be 100% positive class, right? And I got 30% positive class, which I would round down to saying not positive, right? Because it's lower than 50%. Okay, so it's not majority positive, it's majority not positive. And it's wrong. So in order to make an adjustment, I'm going to calculate my error as 1, or the y, right? 100% probability minus the predicted probability, which is 0.3. Okay, and so 1 minus 0.3 is equal to 0.7, right? All right, so is everyone following this so far? Do we have any questions?
Were you say, Jesus, were you saying like it's like 30% right, but 70% wrong?
Yeah, it's 70% wrong.
When you talked about the initial weights being arbitrary, is that the bias?
No.
Okay. Oh,
Weights,
right. That's
weights are randomly generated. Yeah, weights are randomly generated. Bias is typically iterated on. And we'll talk about that in a minute. Typically, it's a static value, not a dynamic one.
That's the only thing. It doesn't have a special term because it's basically irrelevant because it's arbitrary anyway.
Yeah.
Okay.
But there's a whole theory behind getting the right bias value for each of your layers, and Keras abstracts all of that away, so you won't even be messing with the bias value. So for the purposes of this, I'm not even going to include it. Okay. Which typically works. It just sometimes it might not be the right line. Well, we're just getting ahead of myself. All right, so we've calculated the error, right? And we say, well, we were 0.7 off from where it should have been. And now we need to calculate how much we're going to adjust the weights, okay? And here's where we're going to do something a little tricky, and I'm going to abstract this, okay? But at this point, we need to calculate a number which can then be combined, linearly combined, to the weights, right, to change them. And it's going to change both of the weights simultaneously, okay? And the way that we're going to do this is by calculating the sigmoid derivative, all right? So basically, and the reason why we're calculating the sigmoid derivative is because we used sigmoid to get this activated output. Okay, so now we're going to take the derivative of that to adjust our weights linearly. Does that make sense to everybody?
Say it again.
We are going to take the derivative of the activated output, f of x, right, to find the values, right, that are going to change our two weights.
Maybe just not clear on derivative. Is it like in an inverted inverting the significance of the sigmoid function, sort of?
Not quite.
Backward engineering?
No. Get back to me on that personally. I will explain derivative. It's got its own thing. Okay. We need to calculate the value by which we're going to combine with weights 1 and weight 2 to get closer to 1, right? And the way that we're going to do that, we're going to calculate our adjustments. Okay? It's going to be equal to the error times the derivative. So I'll say, I'm not going to actually type out derivative. In case you're wondering, it looks something like dx over dt, I think. I might have that backwards. Spin a minute.
I actually have a question that kind of has to do with that. You're taking the derivative of the activated outputs with respect to the weights, right? Because just like if you were doing like a regular derivative of like a function, you usually do it with respect to. Would you usually be doing it with respect to x or y? So no, actually, it's not
with respect to y in this case.
Yeah. So you're taking the derivative of the activated outputs with respect to not the weights. With what are you trying to? With like what you're predicting, I guess. I don't know. That's where I'm like falling a little bit.
I see. Okay, we're gonna come back to that. Okay, we're taking the error times the sigmoid derivative. I don't want to write this. We'll just say the sig d, right, of the activated outputs, or our probability here. Okay, which in this case evaluates to literally 0.3. Okay.
Is that activated probability another word for prediction?
Yeah, it's literally this number. We're plugging this number in to the equation for the activated output. and taking the sigmoid derivative. Which, in case you're wondering, to find the derivative of the sigmoid, right, we're saying you take f of x, which in this case is 0.3, I'm providing some context here, and then you multiply it. And forgive my elementary use of multiplication symbols here. And then you multiply it by 1 minus 0.3. This is the derivative. This is what this equates to. Okay? This is what we're doing. Make sense? Any questions on that? All right. So we calculated our adjustments, and now we need to actually propagate them back to these weights. And this is where the fun part comes in. How do we do that? What do we adjust the weights by? So we'll say new weights.
Of the adjusted weights and the old weights.
Right, the adjusted weights and the old weights. How do we calculate the weighted adjustments?
Dot product?
The dot product of what?
The adjusted value in the old weights. Right?
Oh,
The adjusted value is X transposed, right? We need the inputs.
What? Okay.
Yeah. So what it is, you take the weights, the original weights, which, oh my gosh, plus the dot product, right? Or I could say, yeah, I'll just do np dot dot. Follow along with this kind of programming idea now. The dot product of the X inputs transposed and the adjustments.
Why transposed again?
Because it's not the right shape. You can't take the dot product of it if it's a column vector, I believe. I believe it comes in as a column vector. So it looks like this. And we need it to look like this.
Oh, separate. Okay, I see. Yeah.
In order for the linear combination for the dot product to be valid. Okay. All right. So these are the new weights, right? So we plug in new weights. Oops. Plug in new weight 1, new weight 2 here, and new weight 1 here, right? And we get rid of these. These have been replaced, right? If we were to loop through this again, we would just follow the same procedure, right? Feed forward, 0 gets linearly combined with new weight 1, 1 gets linearly combined with new weight 2. We take the sigmoid of that, and we get a new probability, right? So that's how it's going to work, and it's going to be higher, right? I can tell you from experience, this number would go up in this particular case. Is everyone kind of tracking this idea of like what we're doing here?
Does it ever go down?
What's that?
The probability. Does it go down?
Oh, yeah, it can. It can. It absolutely can. And if it does, it'll shift the other way. The derivative will change if it goes down.
When you're choosing weights, like with the random generator, like do you have like how are you doing this? Like how are you choosing this random numbers, or like a range of that number is gonna be okay for this kind of data?
Say that one more time.
Like when you're generating the random numbers for the weights, like how are you doing this? Like for particular data, like it depends on the size of the data, or like what it depends on.
You can start with all zeros. You can start with all ones. You can do like I think he does with you guys, where you do this sort of weird 2 times a random number in a certain shape minus 1, right? That's another way. I think it's a pretty popular way of doing it.
Isn't that so we just get a random number between -1 and 1?
You got it. That's exactly what that does. Yeah.
Can you show me the mathematics for this page?
Say that one more time.
I need to see the math formulas for this.
The math formulas?
Yeah.
Yeah, probably. Hang on.
Thanks.
Let me see if this is it. Yeah, here, this, instead of writing it all out, because I feel like it's kind of one of those things that I really don't want to divulge too much time in. But if you would like to take your understanding in the mathematical direction, check this out. I'm going to drop it in DS12 After Hours. But it shows you the whole process, including the linear combinations written mathematically. Okay?
Comparing this to the thing that we walked through in lecture on Monday, and in the step where you're getting the adjustments, I originally had written it similarly, but now I had done it incorrectly, where you're doing the sigmoid derivative of the activated inputs, but in lecture it was actually a sigmoid derivative of the weighted sum. And I ran both of them just now. One of them took like a few times to get the correct output, but using the weighted sum was like first time around. So I'm not sure about if I'm doing that right or not.
Yeah, no, it should definitely be, you take the sigmoid of the weighted sum. Right here is where the weighted sum is calculated, right? You take the weighted sum here.
When you're doing the adjustment, the error times the sigmoid derivative of the weighted sum.
No, it's activated output only. This is what it's supposed to be. Yeah. So the result of this f of x, which in our case is 0.3.
Well, like I said,
literally
I'm not mistaken. He did it with the sigmoid derivative of the weighted sum in the lecture, and like I said, it performed better. So I'm
not 100% sure on how that works.
I'll get back to that.
Yeah, I'm not 100% sure.
Obviously, I don't know what I'm talking about.
This is what I know. This is what I've done, and it works.
I think that has to do with what I was asking about, though, because you're taking the derivative. You're trying to see how, like, you should change the weights to, like, how much the output changes when you change the weights. And so you're taking the derivative of the entire activated output function. And if you had, like, multiple layers, right, you'd have the sigmoid derivative of, like, what's inside. Like, we talked about this in my, I know I'm explaining it poorly because Chris Howell is, like, a mathematician and he was trying to explain it to us. But you're doing, like, the, like, cross product, I think is the name.
Dot product.
No. Like, when you're doing the derivative of two things, like a function that's multiplying two things.
Oh, okay.
So, like, you're taking the derivative of sigmoid, and then inside the sigmoid function is the weighted sums. So you need to take, like, the derivative of the inside times the derivative of the outside, and has to, like, that's what I was kind of confused about.
Okay. Yeah. No, I think that might actually go above my understanding of mathematics. I'm self-taught calculus, and I'm not all the way through it yet. So you could be onto something there. This is the way that I do it. I know that it works, but it might not be as efficient. If I'm understanding what you're saying, Chris, is that you actually need the derivative of both. Is that right? This is the sum of the derivatives of both?
Kind of. So basically you're taking the derivative of the whole activated output, like, function, right?
Mm-hmm.
And in that function, there's, like, you're applying the sigmoid to the weighted sums. So you're taking both the derivative of the sigmoid function and the weighted sums inside of it.
Well, if you're going to do that, then you might as well just take the 0.3 out and just plug in the weighted sums straight into the derivative.
Exactly.
That's just an unnecessary step.
And that's what we're doing.
Oh, that's what you were saying before that you were. Oh, okay, I got you. Okay, yeah, you calculate the error for sure using the activated output. Okay, but if I'm understanding what you're saying, then you're saying when you do the adjustment, you calculate the error times the derivative, the sigmoid derivative of the weighted sums, not the activated output. Huh. Okay. I'll change that in my code and check to see how it runs. But I mean, if that's what's working, that's what's working.
If this is kind of still shaky for me.
It still worked. It just took a couple iterations to get the same performance.
Okay.
Yeah, but Chris Howell, that he's in my TL group.
Yeah.
He has a master's in mathematics.
Oh, I gotta pick his brain then. I got questions.
He's gonna run like a math review session on all the neural networks, like calculus and stuff. So
that'd be bang up. I'd love that.
He was talking about doing it tomorrow, but he was supposed to put up a poll, but he didn't. So
okay,
just kind of heads up for everyone if they're interested.
Cool. All right. Well, then I'll try to stay away from some of the math. Then I would hate to lead you down the wrong path. Again, I'm self-taught in calculus, and I've only just barely made it through derivatives. I'm starting to work on integral. All right. So, I am far from an expert in mathematics, but my basic understanding does lend itself to agreeing that should work. Then, if what you're saying is right about the needing to take the derivative. Okay, yeah, that totally makes sense actually when I think about it.
And yeah, it made sense.
Because it be respects to X, not Y.
Yeah, when I thought about it, how you're looking for what the change in weights does to the outputs.
Right. Okay.
So you're taking it with respect to the outputs, and so you need to take the derivative of the whole function. I'm sure that sounds really complex, but
no, it's actually making sense. Okay, but here's where we're at. The XT still needs to be adjusted. Okay, or rather, I'm sorry, the weights still need to be adjusted, and we have to do that with XT, primarily because in order to do matrix multiplication, right? X here would be in row form. It would be 1, 3, right? And it needs to be 3, 1. Anyone know why? 3 rows, 1 column. Why is that? What wouldn't go here?
1.
What's that? Oh, I'm kind of doing this wrong too, by the way. Hang on. Yeah, no, it's just going to be one number, right? And in order for that to be valid, which gives you back an array. Here, let me show you. If you do matrix multiplication, man, really got to work on my organization skills here. Okay, so if we have xt, right, which in this case is 0 and 1, okay, and we put it in that column form, 0, 1, right, and then we combine that linearly with our adjusted, right, which I'm just going to call z, okay, and what is that going to equal? What shape is this output going to be?
0 plus z.
Well, this is 2 rows, 1 column. And this is 1 row, 1 column. So it's definitely valid dot product. I just did 0, 2. Why did I do that? 0, 1, 1. All right. It's going to be a 2, 1. Right. The outside edges tell you how this dot product is, what form this dot product is going to be in. Right. So our result is going to be, weight 1. Oh, sorry. It's going to be 2 rows, 1 column. So it's going to look exactly like X. All right, so we get weight 1, weight 2, which, if you've already thought about this, is exactly the way the weights came to us in the beginning, right? We're literally putting the weights back in the exact same format that they came in. When the linear combination occurs, it occurs like this. I forgot to demonstrate that. This is the linear combination occurring here in the center part, right? This is how it works. Everybody tracking that? You're just taking the dot product of X and the weights. My apologies for skipping to, or just neglecting to explain that altogether. You have to take the dot product, this is the weighted sum, is the dot product of X and the weights. Does anybody know why it's called the weighted sum, by the way? When you're taking a dot product, you think you're doing multiplication. That's not a sum. All right? Why is it the dot product? Or why is it the weighted sum? Who remembers how to do the dot product?
You add them together in the end, right?
You add them together in the end, yeah. So you're getting the linear combination and you're adding them together, right? The end result, right? If this is a 2-1, bringing us all home now, and this is a, or rather this is a 1-2, my apologies. Right, if this is a 1-2, and this is a 2-1, the result is going to be a 1-by-1, right? It's going to be our activated output here, or our weighted sum. So, or I guess sum of weights, however you want to visualize that, right? It's our weighted sum. Cool? All right, cool. That's the broad level overview, and we got done with that in 40 minutes. So now let's jump into some code. Has everyone had a chance to get from this what they needed to get before I get rid of it?
I just got here. Can you take it from the top?
Oh boy.
No,
oh,
I'm joking.
That's 45 minutes, dude. I'll tell you what, I'll save this thing.
It's recorded, Ryan.
I figured as much. Thank you, Jacob.
Yeah, so you guys can watch me make those mistakes in live. That's great. Yeah. So that's the basic stuff, right? Pretty cool. And this is one perceptron. So a neural network typically is a combination of perceptrons, right? It's a bunch of them put together, right? Kind of imagine that we just explode that out horizontally and vertically, and that's how you make a neural network or a deep learning network, right? But this is the bare bones framework from which all neural networks are based, right? And understanding how these sort of things happen, right? It might not, or we might use a different type of loss function. We might not just take the sigmoid derivative, right? There's a whole number of things that you can change in this, but essentially the steps remain the same. Does that make sense? All right. So now I'm going to pull up my Visual Code Studio, and we're going to code. Actually, I don't want that. I want JupyterLab. I need to do this in a notebook because I'm a dummy. JupyterLab.
So you haven't gone over any of today's stuff yet? I don't want to reiterate questions.
No, but I need to hurry up if I'm going to. So I need to do
I've literally spent
stuff fast.
Almost all day today doing yesterday's stuff too.
Yeah.
I just got to today's homework.
Okay, cool. All right, so here we are in an untitled IPYNB. Okay, so what are we going to need? We're going to need pandas. I need to really hurry up. This is why I need to make these things in advance, so that way I can just kind of go through them, and it's already here. All right. Okay, so yeah, we're going to need import pandas, and we're going to need sigmoid. Hang on. I don't feel like writing it out.
NumPy?
Yeah, I think it's NumPy. Or import. Ah! Oh my goodness. NumPy as in P, and we'll just roll with that for right now. Let's give ourselves some data. All right, so we'll say, oh, no, that's not how dictionaries work. 1, 1, 0, 0. And x2 equals 0, 1, 0, 1, and y is, if x is 1 and y is 2, 0, that's going to be 0, 0, 1, 1. There we go. That absolutely makes no sense. All right, so let's go. I know it seemed like I really knew what I was doing there, but I really didn't, I promise. What is the sigmoid function? Hang on. Oh my goodness. Sorry, y'all. Okay, so we're going to set this up with the regular loop. Or actually, do you guys want to see the loop or do you want to see the class? Which do you think is harder? Or do you need help with? Let me ask that.
What do you mean by what? Specify loop.
The loop is just where we do it step by step, basically, without it being part of a class. No methods, just steps.
Oh, no. I mean,
if we're going to do loop in the class, might as well just do the class.
Okay, that's what I was thinking. Okay, so we'll just do, we'll create the Perceptron class. Okay, so call this class Perceptron. Oh, I don't need to do that anymore. I used to be in the habit of putting object in here like this, but you don't have to do that anymore, I found out. Okay, base.
do you know why? Because I've seen documentation with both, and I've just been doing it.
No, that's just how I, like, originally when I started doing classes, like, that's what I picked up. And it turns out it's totally unnecessary if you don't have a super.
Yeah, it's pretty much 50-50 in any documentation you find it, if you knew.
maybe it's from like older versions of Python. I don't know. Anyways, I digress. We'll define our init. Pass in self and iter, or call this initer actually. Yes, iter is a refined or defined thing, and we'll just set that base to 100. Okay, and that just makes it pretty easy, right? So we have this self.initer object, and then we'll define the sigmoid. And you don't really need to do the double underscore, but I guess it's a conventional thing. Yeah, sigmoid. And you have to take a sigmoid of a number, so that's going to be x. Whoop. There we go. That's right, xp it. X. So this will give us the sigmoid of x. And then if we want the sigmoid derivative, right, then we need to take f of x times, yeah, so it would be return yeah, f of x equal, or we could just say, we could just pass in, no, it needs to be fx equals sigmoid x return. I think this is right. Yeah, f of x times 1 minus f of x. Okay. Which I think can actually just be done with log it. Right? Am I right on that? Is it log it? Let me check.
No,
It's not?
it was correct before.
Yeah, it was correct before? Okay. Yes, we take equals the sigmoid of x, return f of x times 1 minus x, f of x. Which is really fun. You can kind of work that out mathematically, by the way, too. It's kind of fun. All right, so yeah, from here, we just want to define a quick method that's going to get our weights. Really don't even need to do that, actually. Just define fit. self x, y. I want this to be uppercase x, lowercase y. All right, this is where we're going to actually fit the class and do our iterations. So we're going to need a couple of things here. Number one, typically you want to start with setting a seed. Okay, this is for reproducibility. And then we can say weights equals that 2 times np.random. What do we need? We need the shape needs to be of the number of columns, right, in our X feature matrix. So we need x.shape 1. All right, that's going to be the number of columns, because remember, 0 would be rows, 1's going to be columns, right? And we want that to be in the shape of that 1, right, which basically just gives us that single, oh boy, we have X shape number of columns, rows, and 1 column, which gives us this sort of, has this form, right?
So if you weren't going to do a random seed, what would the weights be?
Oh, it would just change every time I did this.
Yeah, but what would you typically put there?
What do you mean?
How do you decide what you want the weights to be?
Right here.
It's just always random?
Yeah, it just picks this random number. This basically says each time that we do this random.
If you wanted to control some of the output, though.
Technically, you could put that in the. All right, so maybe if I just don't confuse you with the random seed, because it's not really that important. At the end result is you're always going to get different weights. It doesn't matter where they start. I'm just keeping the weights between -1 and 1. That's all I'm doing, because after our first iteration, it doesn't matter anyways. They're all going to be changing based on the calculated adjustments, right? Yeah, so best not to just get really that confused. I'm picking this for 2 reasons. One, it seems to be convention in the neural network family, right? This seems to be something that a lot of people show, that's how they choose their weights, but also because it doesn't really matter, right? At the end of the day, we're really just kind of hoping that we get good starter weights. Otherwise, we have to set up, good gradient descent algorithm paired with a good loss function, right? In hopes that we hit our global minimum.
I've just looked for documentation, and I see that often, but it's always used with like the IRIS data set and stuff. Like, I just didn't know why we chose to do that, or when you would not do a random seed or.
Yeah, I mean, I guess you don't need to do a random seed. Or honestly, if you wanted to do a random seed, you really should probably define that up here. And really what it's doing is making sure that anyone else that runs this notebook should get similar results, right? Their weights should start in about the same range. It's supposed to be exactly the same, but it never really works out that way. But it'd be really, really close to what your starting weights were when you ran it, right? Otherwise, if I take this out, then somebody else comes and runs my notebook and suddenly they get completely different results than I did. And that's a possibility. It can happen, right? If let's just say I didn't hit global minimum, but suddenly they got really good weights and then it did, they get completely different results, right? So to avoid that, for reproducibility, you could do a random seed. Okay, that's all that's done. All right. So now we want to go through the same process that we just went through on the whiteboard, right? We have all of the information. We're passing in an X feature matrix and a Y target variable. All right, got like 3 minutes to do this. We're going to take the we're going to calculate. All right, so we've got our starter weights. Take the input. We're going to calculate the weighted sum as being the dot product of the X feature matrix and our starter weights. Okay, this is one perceptron. So we're just going to take the X feature matrix, multiply or combine it, linearly combine it, or take the dot product of that and our weights to get our weighted sum. And then we're going to take the activated output is going to be equal to the sigmoid, right? Yeah. Yeah, sigmoid of the weighted sum. just like that. Okay. So this is what we call the feed forward. Remember that? Did he talk about feed forward and back propagation?
Yes.
Yeah.
This is the feed forward part. Okay. And a single perceptron, it's 2 steps. You get the weighted sum, which is the dot product of the X feature matrix and the weights, and then calculate the activated output, which in this case we're doing that with our activation function sigmoid. Okay. No idea if I spelled that right. Don't correct me. Now we need to work backwards, right? We need to first calculate our error. And how do we do that? Anyone remember? What do we subtract from, or rather, what do we, y minus what?
Activated output.
That's right.
Oh,
So we take the activated output, subtract it from y. That's going to give us the error. And then we're going to calculate the change, or rather the adjustments that need to be made, right? By taking the error and then multiplying it not by the derivative of the activated output, but of the derivative of the weighted sum, right? So we're going to do self dot sigmoid derivative, right, of the weighted sum, okay? Which is different than how I've done it before, so we'll see if it works. I'm not 100% sure. Okay, then we're going to say our weights equals weights plus, okay, the dot product of xt. So now we have to transpose the x, remember, because it's coming in that column form, or rather it's coming in row vector. We need it in column vector in order to get back the weights in that column vector form, right? So it's going to be the dot product of x transposed and the adjustments that we just calculated. Okay? And that's it. We're going to just keep doing that over and over and over again for the number of iterations that we specified we want to do by default 100. Okay? And that's that. Any questions on that part?
Can you say that again why we have to put a double underscore
You
before
don't.
this?
It's just a conventional thing for internal methods. So this method is not for, like, I'm not going to raise up this class and then use the sigmoid derivative. I'm just doing the sigmoid derivative internally.
Okay, thank you.
And that's what double underscore generally denotes. It's primarily there in case, like, if a class that you import has methods built in, prevents namespace collisions. So these methods can't be overwritten very easily. You would have to name whatever you were defining underscore underscore sigmoid derivative, right?
You have a little typo on predict.
Predict? Apparently that's not how you spell. Okay. So now, in order to do a prediction, we're just going to do that feed forward, right? So we've already got our weights, assuming that we've already got our weights right. We're just going to take the weighted sum, and it's just going to be equal to the dot product of x, which, and that needs to be uppercase, x, and weights. I should probably, this really probably needs to be self weights. Sorry. I hate going back and changing stuff like that, but I just realized I didn't put self. This needs to be an attribute of the class. There we go. Yeah, self.weights. And then the activated output equals what? The sigmoid, right? Yeah. Sigmoid of the weighted sum. There we go. All right, so the activated output is the sigmoid of the weighted sum that we just took, and we return the activated output, right? That look right to everybody? Looking pretty good to me. All right, so if we've done this right, we have a class that is effectively a working perceptron. All right, let's try it out. All right, cool. So we've got model. And if we look at that, we've got our perceptron sigmoid derivative, fit, iter, and predict. Awesome. So these are going to be our two methods here, and this is going to be the attribute, right? Which, if we look, it just defaults to 100, right? Cool. So we're going to do 100 iterations on this, and what are we going to train it on? Well, I don't know. We're just going to train it on all of this data, right? And then I'll make up a new set of data. Does this even have logic? I don't know. It doesn't really matter. All right, so we'll take the perceptron model and we'll fit it with X being, oh, I forgot a step. Hang on. And then we'll say data equals, or df equals, we're going to put this in a data frame first. Just make sure I did that right. Yeah, I did. All right, cool. All right. So we'll say X equals df x1 and x2. Or you could just do df drop y, doesn't really matter. And y equals df y. All right, and we see that we get x1 and x2, and then y. Cool. That doesn't really look very good.
Dot values.
Yeah, dot values at the end.
Oh yeah, that's true.
Also, are you adding bias in anywhere?
What's that?
Adding bias in anywhere?
No. Remember, I told you I was just going to ignore bias for this example. But typically, yeah, if you wanted to do bias, you would just add another column. You could do that in your class statically, like add another column of ones and then work with it that way. I was just trying to avoid that because it's potential area of confusion, and I'm covering this from a really high level. Okay, so yeah, we're just going to train it on all this data, and we've got x, y, and you're saying I need to do values here like this.
I think it leaves the parentheses, or does it? Actually, I'm not sure about that.
Oh, that works.
Okay.
Yeah, that's exactly what we wanted to do, by the way. Get those arrays. All right, cool. So we've got x and y, and now we can do model.fit on x, y. And if it works right, oh, it didn't work. Oh, it doesn't have XP yet. What? Hang on. Give me a sec. Let me try to figure out what I did wrong here.
I think it's just EXP.
Is it? Where is the documentation? Hang on, 2 seconds. Where did I get that from? Another, might have got that from SciPy. Yeah, that's exactly where I got it from. All right, okay. What do you mean? What? Can't, oh, because I don't have freaking, okay. What's the numpy? Is it just EXP? Anybody know?
Just for an actual exponent.
Yeah, try that.
Sigmoid is not defined. Name Perceptron sigmoid is not defined. Say what? What you talking about? Oh. Oh, I get it. Makes total sense.
Still have double underscore.
Yeah.
After activated equal.
Yeah, hang on. All right, let's try that. What? What is happening? Oh my goodness.
But during the lecture, we were defining sigmoid different. It was something like a 1 divided by, in parentheses, what was that? 1 plus and p dot x in parentheses negative x. Like,
I think that was accounting for the bias.
Oh, was it? Okay.
Yeah, I believe so. Because he during after hour or during his office hours, he said that you didn't need to do that, and then we ended up going back and doing it anyway. But yeah, that's what we've gotten all of our stuff.
Oh no, it's negative. Yeah, that's what you're talking about. Which is fine. You can still do that. Okay. But why is my class broken? I've got questions. What is wrong with my class?
What's the error?
It's just telling me that perceptron sigmoid is not defined. Where did I mess this up? Poop.
You have not defined that. You have not defined perceptron error, just error.
What's that?
You define just error, no percent sigma error.
What are you talking about? That doesn't. Yeah, that doesn't need to. It's an internal value. It's a local variable. It doesn't need to be an attribute of self. This is the issue. I've never seen this before. Why is it doing that?
So why did you remove self from the sigmoid?
Oh yeah, we do self dot underscore underscore sigmoid.
Well, but that's what it was before.
Yeah, that's what it was before. It didn't change anything. Actually, it's the exact same thing.
Well, you also have sigmoid. You're calling sigmoid above that.
Yeah, right here. And there's another one actually too. Hang on. Self.sigmoid derivative, self.sigmoid.
Down the predict.
Yeah, right there. Same thing. If I look at this, hang on. What the heck is this? Okay.
Do you have it cached somewhere in your memory? Were you playing around with this earlier?
No, I didn't even play around with this earlier. So, I don't know. This is really throwing a wrench in my plans here. What is going on? Why is it named this? Hang on.
Oh, when you also you call the sigmoid function in sigmoid derivative.
Yeah.
I don't think that's it, but you don't have a self there either.
What's that?
In the sigmoid derivative function, when you define that, you call the sigmoid function. You don't use self there. That probably isn't it, but you check.
Could be something.
That helped for me, actually. That made it work. Did you?
Yeah, no, it's still reading these two. I'm trying to figure out why it's prepending underscore perceptron to the method name. It's not supposed to be doing that.
The only thing I can think of is the IDE that you're working in, because I literally have the exact same code that you do right now.
Restart your kernel.
Yeah.
Like maybe the double underscore makes it.
No, everything that I'm looking at it shouldn't do anything special. Like it's only supposed to change, or rather, it's just for PEP 8. It's still doing it. Okay. Well, heck, if I take this out, Let me just remove the underscores and see if that's it.
I mean, I've seen methods and functions where they just literally use double underscores, like nothing else. It's the most confusing thing ever, but
yeah, it can be done.
Or for loops, they'll use an underscore instead of like.
That make any sense to anybody?
No.
Why?
Now
it works. Okay. Well, anyways, I'm not even gonna worry about it.
Wait, what did you change?
I just took the underscores out.
Underscores out.
It took
that's
the,
it.
and
What?
then now they're down here where they're
Okay.
supposed to be. I don't. Makes no sense. Shouldn't change anything, but it does. Okay, so we're back on track. We've got a model now, and we fit it on X, Y, and now we can see those weights, right? We see that we have here's a set of weights and here's a set of weights, right? Pretty cool. So we've got everything that we need. Now we can kind of push through. I'm a little confused.
Maybe there was a namespace collision.
No, it shouldn't have been. Actually, you know what? There might have been. Actually, you could be right about that.
They just appended the underscore.
Yeah, they did underscore and then my class name and then double underscore the method name. That's weird. Okay, so now we have our weights. We can do a predict, right? And if we do a predict, we should get back an activated output. So let's check it. Excuse me. Let's check that out now. So if we do model.predict, and what are our x values? Right, we have they need to be 2, right? So I just need 2 values. I'm gonna plug in 1, 1. Let's see what happens. And we get back 4. Hang on. Stand by. That's wrong.
Should it be 1, right? 1 value?
Mm-hmm. It's supposed to be 1 value. What have I done wrong?
Do you have it as a dictionary or a data frame?
Data frame, and I think the issue is this. No, that's definitely not it. Hang on. I should have known something was off. It's giving me 4 weights back. It's only supposed to give me 2. X shape 1. I'm curious. Is that defined? 2. Okay. Okay. X self.weights. Yeah. Okay. Get the sigmoid of the weighted sum. Yeah. Okay. What the heck? What has gone wrong here? Give me 1 sec, y'all.
Trying to find out why the weights are the wrong shape.
Yeah. Oh, well, that just made it worse. Okay. Cool. Understood. Yeah, the weights are the wrong shape and they shouldn't be. It's just throwing me. Take the dot product of x and self weights to get the weighted sum. Maybe. No, that doesn't make sense. I'm gonna try it. It's gonna fail.
I've only seen that
Yeah.
in the bias is when you'll use the transverse.
No, yeah. No, it's not. Well, like, even before I did it, I was like, no, that doesn't seem right.
I have been doing stuff like that, but yeah.
This is embarrassing, y'all. Why has this happened?
I think it's a transpose error.
It's not, though. It's not. Where am I getting? Okay. I hate doing this, but all right. So we're gonna work this out. we're gonna break this out now. Okay. We're gonna do this step by step. That's the best way to do this. All right. So our inputs are gonna be these. Okay. So let's just do this. What is x? Okay, x is 0, 1, 1, 1, 0, 0, 0, 1. Okay, cool. All right, first thing that I do is I define some weights. So let's go ahead and do that. Weights is nothing yet. Equals 2 times mp.random.random. I guess this is pretty good, right? So a couple of you guys had the same problem, and now I'm starting to see that it maybe is not quite as simple to fix as I originally suspected. So we want x dot shape 1 by 1 minus 1, right? Then we can look. Okay, this is the correct shape. Okay, so weights is right. We don't have to worry about weights. Good deal. What's next? Right, the next step is going to be to feed this forward. We're going to take the weighted sum. We're going to do the mp dot dot of x and self weights. All right. Okay. And we get this back. Okay. So now we've gone from, so we had, so it was a 2, rather this is a 2 by 1, and that weights was a 2 by 1. Yeah, weights is 2 by 1. And this is 2 by 4. That doesn't make sense. It needs to be a 1 by 4 or 1 by 2. Yeah, it is. It is. Okay. So basically we're getting different weights back for each iteration. Right, so the weighted sum for each of these. Oh, I think that might be the problem. I think that's the problem. Yeah. 2, 4. So before it was 4 by 2, 4 rows, 2 columns by 2 by 1. Okay. All right, let's roll with it. This is what I had. So we had the weighted sum was x times weights. All right, so these are our weights. Apparently we have 4 weight. No, this is our weighted sum is an array of 4 values. Then we take the sigmoid of that. Sigmoid again is this. So we'll just do 1 divided by, all right, so activated output equals 1 divided by, is it 1 plus? 1 minus, yeah, 1 plus. mp.exp negative x. Oh, whoops. There we go. Okay, so this is our activated output. And now we need to feed this back. Okay, so that's going to look like the adjustments. Error is going to be, rather make sure y is defined. Yeah, so error equals y minus The
The
derivative.
values of y must be in brackets. I was having issues like you have now, and I figure out that if I put the values of y into brackets, it works. Each value of y, put it into brackets.
What do you mean?
It needs to be a list of lists.
I posted.
It needs to be an ND array.
Yeah, I put something.
Okay, it needs to be a two-dimensional array. It's a one-dimensional array right now, right? Is that the issue that we're having? That's exactly the freaking issue we're having. No. There we go. Like that?
Yeah.
Okay. Okay, got you. All right, so I have an idea. That turns it into, yeah, that's the only place we use it, so that's the only place it matters. Okay. I'm still, okay, no, I'm still getting the same thing. All right, so I'm going to take the activated output, calculate the adjustments, equals the error, oh no, I'm sorry, the error equals array y minus, or rather, yeah, times, nope, minus the activated output. Okay, and then what is the error? This is the problem. This is wrong. Doesn't change no matter what I do. This is wrong. This is why we're getting a the four things back. Huh. Okay. This should be one value. This is supposed to be one number, not a list. Why am I getting a list? What have I forgotten to do? Can anyone go back and check the weighted sum and make sure that this is right? The dot product of x and the weights. This is what I was pretty sure it was.
That's right.
Why am I getting a list, an array back for my activated output? That should be one number. Yeah, that should be one number. What is the deal here? Huh. Hang on. I didn't change anything.
Why are you saying one number? Like during the lecture when we had the also like a little data frame, it was also giving the four outputs.
What?
Like during the lecture, like when we were breaking down for the steps, everything what we were doing, like activated output also had a four, like array was four values because I mean lists. It was four values anyway. and we had the same NP array as you do. I mean, different numbers, but same shape. Do you understand what I mean?
I think so. The problem is that when I do a prediction, I'm getting 4 results back. I should only be getting 1. That's the problem. And the reason why is because when you calculate the error looks like this. And this is just wrong. Huh.
Wait, shouldn't the activated output just be the sigmoid of the weighted sum? What is all the other stuff?
That's sigmoid
Oh, okay.
of the weighted sum. Hang on. So I'm going to do what I always do when I get stuck. Go find a working example. So let's type it in the chat here. Check that out. Where did my chat go?
Actually, I think I had that problem before, and it's probably because I used the x dot. Then after I switched to numpy dot transpose x, it worked.
Yeah, I've been using everything that you wrote, but I just transposed the NP array for y, and it came out with a singular output.
Hang on. Like, not this. This? Is that what you did?
No, when
That
I
didn't
defined
work.
it.
I had to use np dot transpose.
Okay. Hang on. So let me see if I understand what you're saying here. Hang on. np.array df of y. Okay, which gives, okay. Which gives you the column rows. It should be 1 by 4. No, 4 of 1. Well, that's what this does. Hang on.
If you just use
1 of 4.
NPRI, just make a list of a list. If you use the weight I give you, it makes a list.
Yeah,
of
your targets are still wrong.
That's what we need.
Yep.
Yeah.
That's
Oh.
what he was. The way
Back-
Jesus is telling you is that I think you'll get the same thing as well, though. But it won't be transposed.
Yeah. There we go.
I knew it.
Son of
It
a
was
gun.
a transpose error.
It really was. Or rather, Y was in the wrong shape, as it turns out. Oh my goodness. Oh my goodness. I'm so mad right now. You guys have no idea. I'm so mad right now. Okay. Anyways, so we've got this back. Okay. So for 1-1, it predicts 11% probability of positive class, which means it would be 0. How would we do that? I'm gonna like just real fast segue back into what I was actually trying to do and just pretend that this never happened. Okay.
What happened?
Exactly. So anyways, how would you do this? Well, you could say that, okay, if you have any, this prediction here for 1-1, you could say, here, we could do ypred equals model dot predicts, and you could just assume, right, or rather imagine that we had a bunch. Let's do 1-1, 1-0, 0-1, 0, 0. So we'll just do a permutation of pretty much all possible combinations to get a ypred. Say what? Oh, this needs to be any list. There we go. Yeah. So now we can look at ypred, and we gave it 4 things to predict, and we got 4 back. So you can see we have these weird numbers, right? They're not making sense. So we could do list comprehension, okay? And we'll say that, well, anything over 50% is going to be, is going to be positive class, right? And if it's at 50, now this is important because we actually do have a case where it's exactly 50. I'll say equal to or greater than 50% is positive, else negative, okay? So I'll say 1 if, 1 if x greater than 0.5 greater than or equal to 0.5 else 0 for x in y pred. All right, and there we go. So the last two are ones and the first two are zeros, which ironically is exactly the same thing that we got up here with a different set of numbers. Fun fact. All right, everybody tracking that? This is yesterday's work.
Brandon, will you do the show share that over towards the end? I just couldn't keep up with the changes.
Oh yeah, no doubt. Yeah, I was doing a lot there while Jesus was patiently trying to tell me what my problem was, but I wasn't listening. Thank you, Jesus, by the way. I apologize that I was not listening at all. But there we have it, right? And now we have our activated outputs. At the high level, this is what's happening in the perceptron, right? We're getting our weighted sum and our activated output in the feed forward process, calculating an error in the adjustments, and then making changes to the weights in back propagation. Okay, cool. So for today's assignment, we needed to do something more back propagation focused, right? And actually make multiple layers using TensorFlow. Is that right? So let's talk about more specifically the back propagation part. Okay. I've got 30 minutes. Let's actually pause here and let me collect questions on this part. Here's the perceptron class in case you need to see it. Let me take some questions. Goggin, are you asking a question?
Yeah, I was kind of confused. Like, well, how do you know what kind of shape you had to return it in? The prediction.
Oh, the prediction? Yeah. Well, it's just I'm kind of using a little bit of common sense here. I was like, I'm giving it an x, like two x values. I should get one y value back for two x's. And then I was getting 4 back, so I knew something was wrong, right? Like that's not, something was not in the right shape. And luckily we figured out that it was the y was not in the right shape. Yeah. Any other questions?
If you don't want to talk about this, then like I'm okay with it too. But so I tried to implement basically the same exact thing for yesterday's assignment, and like I've been talking to my group in my TL, and our conclude like my perceptron is predicting the same outcome for every single input. And we thought it was because I didn't have any bias. So I put a column of all ones in that it's like just another column, and I'm still getting the same thing.
Is it predicting all zeros or all ones?
It was predicting all zeros, and now that I added the bias, it's predicting all ones.
Yeah, okay. Looks like the weights aren't being updated correctly.
Okay.
That's what it sounds like. Anyways. Did you use a single layer perceptron to do it?
Yeah, I pretty much did the same exact thing we did here.
This class, right?
Yeah.
Yeah, it's not going to work. You need a multi-class.
Well, I did an iteration like in my fit function.
Mm-hmm.
Oh yeah, actually, yeah, it's the same thing. Yeah.
This exact same thing, the perceptron class. Yeah, I don't think it's going to work. I needed to do another layer in order to get it to do anything.
So did that happen to everyone, or am I just like the only one that did it, or like?
No. We had another person who also had the same problem.
I have the same problem.
Yeah.
I did a bias, and then prediction is always one.
You should be able to get about 60% accurate predictions with both classes. However, I think the perceptron is not going to be able to handle that many inputs. Okay.
So it's basically like, because there's only one layer,
it's just input straight to output, and it's just like, well, this is all I got. And you're just getting zeros or ones for everything. We can implement a multi-layered network, which is not much harder than what we've already done. In fact, to demonstrate this, I'm going to copy and paste. Okay, just for that reason, to show you how this changes. Okay, but now instead of it being called a perceptron, I'm going to call it a basic neural network. Okay, we're going to do a multi-layered. Yeah, we're going to do multi-layer here. I don't want to do this. Da, 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 da. I want to say, okay. In the init, I want inputs, just set that equal 1, hidden equals 3. No. How many hidden? Let's do 4. Okay. Don't worry about these numbers right now. Okay. All right. So I'm going to do self.inputs equals inputs, self.hidden nodes equals hidden, self.output nodes equals output. I'm going to set some initial weights. So instead of doing that here, I'm going to do that here. Okay. I'll say self weights 1 equals the 2 times np.random.random. Oh, I could just copy this actually. V. Yeah. So just copy. This is going to change. Yeah, this is going to change. So instead of it now being it's going to be self.inputs hidden nodes -1. Yeah. Does everyone see what's happening here?
Why
What
do
am
you
I doing?
have 2 equal signs?
Oh, that's because I copied and pasted it, and then I was like reading back. This is why I'm so against copying and pasting. Freaking mess stuff up. There we go. Yeah, so weights 1 is the first set of weights, okay? And that's going to be equal to, again, we're just setting up that random value. But now, in order to get our dimensionality right, it needs to be the number of input nodes to the number of hidden nodes. Why is that? What am I doing? What am I specifying that it needs to do? Connect every node in the first layer to every node in the second layer, right? All right. So I'm going to have
a 1-to-1 relationship there.
Every node will be connected to every other node. I'm creating a dense layer is what I'm doing here of weights. Okay. So inputs here in this case, if you were working with the same problem from your assignment, which I think is what? The
diabetes. So.
Yeah, diabetes.
There's 8 columns, 8 feature columns, 768 observations. So,
well, yeah. No, you can do this with a single perceptron. What am I thinking? Pretty sure you can. Okay. Yeah, we'll just roll with this. I'm giving you an example of a multi-layer. Yeah, so you have to set this up. So you're gonna have 8 inputs, right? You know, 8 input nodes to 4 hidden nodes to 1 out nodes. Make sense? We tracking on this? All right. Now in the fit.
Just to fix this second weights, in the parentheses, you wrote hidden nodes wrong. Like this has to be underscore under.
Oh yeah, thank you. So now we're just going to make a few changes, right? When we pass X in to our fit, what needs to change? Who wants to take a stab at this? What do we need to change here? We're taking the weighted sum of the first layer, or first set of weights. So we're going from our inputs. Here, hang on. We're going from, from inputs. So we got 8 of these bad boys, right? Going to 4 in the middle, going to 1. All right, so we're doing this part.
Change self.weights to self.weights 1.
You got it. This needs to change to self.weights 1. All right, and then we'll take the activated output. No longer becomes, it's not the activated output anymore, right? We still need to do sigmoid because each of these is going to be sigmoid, right? Still got to get the F of the weighted sums, right? To pass on to the output node, okay? So this then becomes not the activated output, but the activated hidden output, right? And we take the sum, or take the sigmoid of the weighted sums. Okay, now we need to add, so this would be from input to hidden layer, right? And now we need to go from hidden to output. What are we going to pass in here? This is the tricky part.
So even though we have 4 hidden layers, we can just go to output now?
What's that?
Even though we have 4 hidden layers, we can go to output now? Or is it just 1 hidden layer?
It's only 1 hidden layer.
With
4
nodes.
nodes.
Gotcha.
Mm-hmm.
So you would use the activated hidden and then the weights 2?
Yeah, you got it. Pretty simple. Or it's not self. Whoop. Take the activated hidden and self.weights 2, right? So this was the first set of weights, right? This is the second set of weights, okay? When we pass from input to the hidden layer, we combine with the first set of weights. Then we pass from the hidden layer to the output layer, we combine with the second set of weights, right? And so following the same basic logic, what is the activated output going to be?
Sigmoid of that.
Of what?
Weighted sum 2.
Weighted sum 2.
There you go, right? Now we need to do this in back propagation, right? So we need, I wish I could move this whole thing. I don't think I can. So we need to do back propagation now. So now we need to go from the output back to the hidden layer, right? And calculate the adjustments for the second set of weights. So how are we going to do that? We're going to take the error equals what? I should say, really, this is the output error, or I'll say stage 2 error, right? This is stage 2. Let me be clear about this. This is stage 2. And this is stage 1.
Is that including that layer?
It's the whole process from here to middle is stage 1, and then from middle to out is stage 2. Okay, and I'm just saying that because that's how I'm doing my naming convention. So my stage 2 error is from my known y minus the activated output. All right, so I'm saying y is supposed to be whatever, right? And I'm using that to calculate the error. Okay? Everybody make sense? Tracking that part? This part doesn't really change, I'm just changing the name. Okay? The adjusted, or stage 2 adjust, we'll call it, equals the stage 2 error multiplied by the derivative, sigmoid derivative of the activated output. Now it's going to be the weighted sum. So we'll take the second weighted sum, right, from stage 2, moving from this node to these nodes, okay? And then we're going to add stage 1 error. Now, time for the trick question. What is stage 1 error? Anybody know?
It's going to consist of the weights from stage 1, right?
No.
It's gonna be stage 2 minus hidden, activated hidden.
This is a trick question, y'all. I'm so sorry. It's actually the dot product, right, of the stage 2 adjustments, or rather the stage 2 adjustments. And the transpose of of weights 2. To get the error. Because we don't, this is different, right? Here we knew what this value was supposed to be, right? We actually have to calculate the changed value here, right? And get that array back, which we can then pass on to say that the stage 1 adjustments will be equal to, this is the stage 1 error. We'll say stage 1 error multiplied by the self-sigmoid derivative, of the activated out, or actually should be activated hidden, which in this case, no, it's going to be the weighted sum because we changed that. Keep wanting to go back to that damn activated output. Okay. So following the same convention as before, right, where we did self.weights equals self.weights plus this is would be equal to that stage 1 error, right? We're going to say that the stage 1 adjustments, or rather this is equal to not adjustments, but stage 1 adjustments for weights 1. And self.weights 2 equals self.weights 2 plus the dot product of the activated hidden here. Yeah. And we need that to be also transposed. And stage 2 adjust. Everybody tracking that? This might be confusing, and I am open to questions.
You explain.
Why are you using?
Here they come.
You go ahead, John.
Can you explain the stage 1 error again?
Excuse me. Yes. So from one value back to where we came from, right? We take the transpose of the known values and subtract that, or subtract from that, the activated output, all right? Which is that the sigmoid of the weighted sums, right? We don't have this value from here to here, right? From hidden to input. So the way that we calculate the continuous error is by taking the dot product of the stage 2 adjustments, right? And the stage 2 weights that we started with transposed to get us back into the right shape.
Why weights 2 and not weights 1 if it's stage 1?
Because you need the dot product, or rather you need the total linear you need the combination of from here to here, right, in order to calculate this error using the adjusted values by weights. We're going backwards, we're not going forwards. And we're trying to figure out what the weights, how much these weights need to change by. How can we use those in that calculation? That makes sense?
But you're not specifying any of the weights values from stage 1 at all. You're only specifying the weights from stage 2.
Mm-hmm.
Just transpose.
Because that's the flow. Listen, you go from Y, maybe this will make more sense. You go from Y, which is all the way the farthest to the right, right?
Yeah, right.
Back to the output to get this error. And then you go from here to here, right, from the output to the hidden layer to get the adjustments. Well, what are you going to use to adjust the weights for weights 1? You're going to use the dot product of the stage 2 adjustments that were calculated using Y, right? You have to use this in order to get the error for stage 1. You can't use the stage 1 weights to calculate the error for stage 1. Does that make sense? Just the same way you can't calculate the error of the output node using weights 2. It comes before that has been calculated. And this has just become a mess, so I'm just going to get rid of it now. Okay? But basically, you go from Y here at the end to the output node to the hidden node, or to the hidden layer, then to the input layer in back propagation. That makes sense? So you can't use weights 1 to calculate the stage 1 error. You have to use the combination of the adjustments that were calculated in this motion multiplied by the stage 2 weights themselves.
So the default weights for
weights.
stage 1 is never used ever again? Like it's never touched at all?
It's never used in calculation. It's the leftmost operation. It's never used in calculation again until we're doing feed forward again.
Okay, I guess that's just some mathematical.
That one's a little tricky. That's a little tricky to kind of wrap your head around, so I totally understand the confusion there. But you can't use the stage 1 weights to calculate the stage 1 error for the same reason you can't use the stage 2 weights to calculate the stage 2 error. Notice that we used the activated output and Y, right? So again, this is the activated output and this is the Y.
Yeah, the stage 2 stuff makes perfect sense. Like I understand all that.
Listen, what I'm telling you, the action of calculating the stage 2 adjustments is the activated output in this part of the function. And the act of, or rather the weights themselves, the stage 2 weights are taking the place of Y, so to speak. Now, it's not the exact same function. We're not subtracting the activated output from Y this time. We're taking the dot product of it. It's still some function of this and this, basically.
So the weight from stage 2 is already going to be closer to the right answer than the stage 1 weights. So could that be also a reason why you want to use?
It's not necessarily that it's closer to the right answer. It's that it's part of the calculation in back propagation. It's maybe someone else can explain that one a little bit better than I can, possibly. That's somewhat confusing, but it has to do with the mathematics. It's simply not possible to incorporate the stage 1 weights in the calculation for the stage 1 error. That's basically what I'm getting at here.
You'd have to go back and undo everything you did.
Well, that's essentially what we're doing. We're just changing what we're combining to find that error. Because we've already used y to calculate. We used y to calculate this adjustment, right? Or this error. And so y, then it becomes sort of represented in this array, right? And if you combine that with the stage 2 adjustment that we calculated using y, then we figure out what we need to change these weights by. So that's how we.
The error isn't even an error really at all. It's just how much we're actually changing the weights by.
Oh, no. I said that wrong. I'm so sorry. It's the hang on. It's the values that we need, or yeah, it's the values that we need to multiply by the sigmoid derivative of the weighted sum that we calculated here. So this weighted sum right here, right, in each of these, in this function of x, needs to be multiplied by a value. And calculating the stage 1 error is taking this array, multiplying it by, or rather, taking the dot product of this adjustment that we calculated and the stage 2 weights, but just transposed so that we get a single number back to get the error number. That makes sense? I feel like I lost a lot of people there. This one's tough. This is really tough stuff to understand. But basically, once we've worked our way all the way back to the beginning, we do it again, right? We change the weights by the two values, right? The stage 1 adjustment and the stage 2 adjustment for weights 1 and weights 2 respectively. And then when we move to the predict, we just have to add the next level, right? So you have the weighted sum, excuse me. Yeah, the weighted sum, and then it's not the activated output anymore, it's the activated hidden, right, by the weighted sum. So we're doing this part, and then from hidden to output.
Would it be equals or plus equals for the weights, for the new weights at the bottom? Because
yeah, so I've seen this, and I've also seen that you shouldn't do that. But this is essentially equal to doing it this way without this being here. It's kind of hard to explain. Python thing. You can do plus equals, or you can do equals itself plus. They equate to the same thing.
Oh, I didn't see the weights one.
Yeah.
So I didn't see that. I see why you did that.
So I could take this out and then just do plus equals.
And then do plus equals. Yeah, I didn't see that you also included weights 1 in there.
Yeah. All right. So then we have to add from activated hidden. We need to do the same thing. So we're just following this feed forward again, right? 2 equals np dot activated hidden self weights 2, right? Oop. And then activated output equals self dot sigmoid of weighted sum 2. Okay. And then we return activated output. All right, so I can get rid of all this nonsense. Okay. This is a perceptron times a perceptron, basically. Right. So we've done from one perceptron, or rather from one layer, not just to an output, but from one layer to another layer to an output. Okay. And this would go for any number of hidden layers that you had. This would hold true. You would just continue to copy the same basic process over and over and over again until you got to the last one, which would then be activated output. Does that make sense?
Can you share that function or like that notebook at some point?
Yeah, I'll share the whole notebook. That's fine. But now we can test it out. So hopefully, now that we know how to accurately calculate the errors here, we can actually try this out, right? So we're still fitting on uppercase, yeah, the X feature matrix and the Y target vector. So in this case, we still have X, which is this, and Y, which is that. Awesome. So if we wanted to work this out, we could say model 2 equals basic NN, and we can just, yeah, defaults will work. Typically, you would specify this, right? Like, okay, for this problem, it's actually not going to work, so I need to specify inputs equals what? Well, we have two inputs, x1 and x2, right? Hidden. I'm just going to up that to 4, keep it at 4, and outputs. Is it outputs? No, it's just output. Output equals 1. This is the number of classes, or so 1 for binary, and if it's anything else, it's not going to work anyways. For reasons that I'm just not even going to try to get into right now. Inputs, we have 2 inputs and we want 4 hidden nodes. All right, let's roll with it. All right, so we've got our model 2. Just like to double check, yeah, make sure everything's right. Good deal. Okay, then we can do model 2 dot fit xy and ypred2 equals model 2 dot predict, and I'm going to do the same thing here. Okay, so here we had, this was our ypred, right? See those values? Let's see if this performs any better. Oh, I forgot to change this.
In the predict function, self.weight.
Yeah, there it is. Thank you. Okay. Looks to me like it did quite a bit better, don't you? Don't you think? It's definitely a lot more confident about this last one. Looking pretty good to me. But it didn't actually perform a whole lot better, probably because my problem was not very well defined. Let's try a different problem, right? Let's try that. Giggity biggity. Where is the stuff for that? Here it is. So I've actually pulled it up over here for the diabetes data set. Now, one of you guys were talking about you were getting predictions for all the same value. All right. So here we go. And I know it's overtime now. I apologize for running over a little bit, but I'm going to work this out. So using this Perceptron, I'm going to try to predict the outcome, right? That's my goal, right? So I can say, well, number one, did you normalize? Or did you just run the data straight through?
I normalized and then added a bias column as well.
I'm gonna.
I have it ready if you want me to send that in.
I'm just trying to remember stuff. It's been a really long time since I've done anything. Is it min-max? Yeah, min-max scaler. There we go. Thank God for autocomplete. All right. So let's say yeah, features equals yeah. I'm doing a shortcut.
It still has diabetes in it.
Oh, outcome. Still got outcome in there. Why is that? Oh, I've got this wrong. Hang on. And target equals
The same thing without the colon.
yeah. Oh, that is not a thing. No. Well, this just needs to be. I was trying to be fancy. There we go. And it's still picking that up. Why is it picking that up? Okay. Well, you know what?
You need to do the indexing outside of like the list.
Outside of the list. Oh, yeah. Hang on. There we go. Good call, man.
I already have. That's exactly how I did it because I was.
Oh, is that how you did it too? Awesome. Okay. All right. So yeah, we got list diabetes. What's that?
John Cody had done that, or maybe the example he showed us did that. So.
Really? Okay. Cool. Anyways, so now we need to get the normalizer equals, or rather, I'll call this a scalar because it's not normalizing, it's scaling. Scalar equals the min-max scalar, and then we'll say equals fit. We need diabetes. Oh, we need to fit transform this. Diabetes features, right? And y equals diabetes target. There we go. You can take a look at X scaled now. It's going to look a little bit different, right? We're still basically getting the inputs, and we can take a look at the shape of this to confirm that we have 768 rows and 8 columns. Now you're going to need to do a train test split on this, so I'm going to do that for, you know, it's just good science. Just do the train test split. Oh, no, not equals. What? Import train test split. And then we'll say X train, X test, Y train, Y test equals train test split, test size equals 0.25. Let's do a quarter of it. Did I do a seed? I already did a seed. Okay, yeah. All right, cool. All right, so run that. This one we're right. Oh, whoops. My bad. Scaled Y. There we go. Okay, cool. So now we can kind of run this. We're gonna train this model on the training data and then score it on the test data. So for that, we'll need metrics import accuracy score. All right, and now we're ready to actually work this out. Let's try it with the Perceptron first, right? We'll say model equals Perceptron, right? With our standard running data, and then we'll do model.fit on X train, Y train, right? Then we're going to need to get ypred equals model.predict on X test. And what do we need to do to ypred to get it back into 0-1 format? Anyone remember? What do we need to do?
You're talking about the list comprehension?
Yeah, we got to do that list comprehension, right? We need to get it into zeros and ones because right now it's in predicted probabilities. So we'll say 1 if x greater than or equal to 0.5, else 0 for x in ypred, right? There we go. And now we can do accuracy. So we'll say accuracy equals accuracy score, ypred, y-test, right? Let's run it. 64%. So let's take a look at ypred, right? All zeros. This is what you saw, right?
Yes.
Yeah. So how did we get 64% accuracy? What's our majority class?
64%.
Yeah. Yeah, exactly. So I imagine, right, that if I did y-test, you know what, I'm not going to do that right now. 64% of y-test is zeros, right? And this Perceptron could only figure out, okay, well, I don't know, I guess zeros, right? Make sense? Okay. Now let's try it with the other model. Model 2 equals basic NN. And we need inputs equals what? How many inputs do we have? 8. Sorry about that, guys. Inputs equals 8. Hidden equals 8. Output equals 1. Okay? I'm going to say niter. I think it's niter, right? What did I put? Yeah, niter. And I'm going to do 1,000. Okay? There we go. Model 2 dot fit. X train, Y train. Right? And then we need pred equals model 2 dot predict X test. And then we need to do same thing, right? Equals 1 if x greater than or equal to 0.5, else 0 for x and y pred. And then equals accuracy score, y pred, y test. Run that. And then we can see that it did no better. Could not figure it out. Pretty cool, right? This didn't even work. So
you try adding the bias. I put like the little method for how I did it there, but I don't know.
Oh, where did you put it?
In DS12 After Hours.
Okay. Let's take a look. Yeah, you can try, but I don't think it's going to fix it. Yeah, it's just not doing it. We can try bumping this up a little bit. Hang on. Maybe get any ones? None. Nothing changed. Okay. Yeah, no. I just don't know that this can do it. Pretty interesting. Has anyone actually gotten something other than zeros in their predictions? Out of curiosity?
I have.
You did?
Yeah, I got a 76%.
Okay, can you share your code with us? Because I'm curious.
My YPRED, the only thing that I changed, Jonathan Duke had us change the return. And here, I can't talk right now.
Did you change the step function?
Yes. No, it was I did it in the predict function or perceptron. Sorry, class. Holy crap.
You trying to share screen?
Yeah.
Now you can. Show us what you did. I'm curious what the threshold was set at.
Right here. That's the only thing. I was just following along up here with you, and then I got 76. The YPRED.
Okay, so hang on. Let me see your function again. Return. I can't see it. I still can't see it.
Oh, you still can't? What?
I see predict, but I can't see the bottom. Wait, where are you going? There you go.
That's right here.
Yeah, good.
I made my screen bigger. I figured it would fix it.
Oh, I can barely see it now. Okay, there we go. So yeah, okay, so you got what in the world? Okay. For XI target and zip XY and delta. Ooh boy. Okay.
You did what was in the example from.
Yeah, and he said that he didn't really want us to do it this way, but It worked.
Yeah. It's a very confusing way to do it. NP dot X self weight predict self return NP where self okay. Okay, return NP where self.net input X greater than or equal to 0.5, comma 1, comma 0. Going, okay, hang on. Looking up the documentation. NumPy where condition X, Y.
I forget exactly why he said that, but because I'm trying to remember exactly. I don't remember even what the original was. It was like 0.1, 0, 0, negative 1.
Huh?
Yeah. So what he, oh my gosh.
Original was 0.0, comma 1, comma negative 1.
Negative 1. Okay, yeah.
I'm still trying to wrap my head around what this even does.
Where is exactly the same as yours. It's condition if true, or condition, comma, if true, comma, else.
That is the same as this?
Yeah, his list comprehension is the same as that where.
I think that's. It seems like you have to think, why is there multiple weights when this is a single layer?
I
don't know what that's for.
I don't know. I was messing with this too.
Let me see something. Hang on.
Like, I think the different weights that you're doing in that for loop might have to do with the bias, but
it does. I do know. I'm pretty sure that's definitely the case. Because then some people had to concatenate, and I was trying with it, and it was just my code wasn't working with it. It kept getting hung up on it, so I just got rid of it again. I don't even think that matters because it's just getting written over it anyway.
Okay, it's very confident that these are zeros. That's some serious zero action. Yeah, that your code is nothing different than what I've done.
Well, it likes me more than.
I guess so. That's really kind of weird.
Well, he does have.
Could it be the random state?
42.
But there definitely is bias put in there. You don't think that would make it better?
No, I don't think it would change anything. I mean, it could, but I don't think it would. Okay. Well, I mean, this is the proper implementation. I mean, we could try it on another issue or another problem. I'm pretty sure it works.
I've literally just been like trying to break this thing apart and really try to learn this. I don't know. I don't even know if I'm absorbing anything anymore, but
yeah. Well, did you use the min-max scaler or the or some other normalizer?
No, I used a regular normalizer. I actually just deleted it out when you did the min-max scaler.
Okay, so then you did that.
This is how I broke up my data the first time.
Okay, yeah, that's one way to do it.
Yeah.
That doesn't make any difference, though.
I didn't think it did. This was just more intuitive.
Yeah. Well, I know it solves the XOR gate because that's a real problem. Hang on. So let me show you that real quick. So this is how I know that my class works, okay? Because trust, guys, I didn't just do this and go, yeah, I got all zeros. It works. It does work. Hang on. Hang on. Go back up here. Oh, I'm not sharing my screen anymore, am I? Okay. So let's look at another example real quick. One where my freaking class actually works.
We're not sharing.
Here we go. So this is an example of something called a XOR gate. Okay. It requires a multi-layer perceptron to solve. A single perceptron cannot solve it. Okay, fun fact. So this is going to be 3 inputs to 1 output. No bias term. Okay? Everybody tracking that? Cool. Crickets are very loud. So we'll say features. No one saw that. Features equals the XOR gate, right? X1, X2, and X3. And target equals XOR gate Y. Cool. So now, yeah, we're just going to do the same thing. Model equals basic and N. And we're going to have 3 inputs. I'm going to do 4 hidden nodes and 1 output as normal for binary classification.
Posted my Perceptron if anyone wants to try it.
Yeah, awesome. Yeah, so say fit on XOR gate features XOR gate target. Right, and we'll do 1,000 iterations. Yeah, looks good to me. What? What? What's the issue here? Pinned. Okay. Fit. What?
Features must be a list of the main.
Oh, I'm dumb. Getting tired, y'all. I apologize. Oh, fit got an unexpected because that's not supposed to go in fit. That's supposed to go in the in it. Oh man, I'm getting tired. Okay. Promise we're almost done. Oh my God. Come on. Come on. There we go. So as you can see, it has accurately solved the XOR gate, right? We're getting 0, 1, 1, 1, 1, 0, 0. 0, 1, 1, 1, 1, 0, 0. Okay. So it does solve a problem. I'm not sure why it doesn't work with the diabetes data set. It should. But yeah, apparently it's just defaulting everything to 0. That's pretty interesting. And I'm actually kind of curious. Hang on. So if I'm having a thought here. I wonder how it would work if it was trained on all the data. So let's take. What's that?
I trained on all the data and I got the same.
You still got the same thing? That is weird. Okay. I might play around with that some more, try to figure that out. But, this is just demonstrating that it does actually work. I'm not sure why it's failing on the diabetes data set yet, but it does actually work. Cool. Yeah. So we did a lot, though. This I think actually you don't do until tomorrow. I think I might have shown you something for tomorrow, actually. The Perceptron class was for today.
I originally, before I did the train, because I didn't train test split originally, I was getting like 60 something, 62%, 64% or something like that.
It should be 64.
Yeah.
That's all zeros.
And then when I just was following along with you, it just 76.
Maybe it is random, the random weights. Maybe it's getting stuck.
I could try different.
Or maybe it's too many input. There's a whole number of things it could be, honestly. I don't know off the top of my head what it is. So we'll figure that out.
The baby's going to wake up at like 5 o'clock today. I already feel it.
Awesome. I appreciate y'all's time today. We covered a lot. We went a little over time, so I apologize for that. But, hopefully this has been at least somewhat helpful. Right? Does anyone have any questions following up with everything that we talked about today?
Can I just take a look at the XOR problem again?
Yeah, actually, let me go ahead and save this notebook. I did not originally anticipate for it to be so long, but now it is, I guess. And in fact, I'm just going to send it. I'm going to paste it in Slack with the pip file stuff too. So let me just rename this to after. Let's call it after hours Tuesday.
I just got 77 changing the random states.
Yeah. Okay, so it's got to be some factor of the random weights that are being calculated, maybe. Yeah, I'm not terribly worried about it because again, it's a perceptron, right? If I really wanted to solve this problem, I would throw something a little bit better at it. This kind of gives you the basic idea. So where is this living exactly? Need to go find it. 1 sec.
Apparently 454545 is an 80%.
Interesting. You're getting up there past what I thought would be possible, which is really interesting. So we need to
maybe something else is broken. Maybe it's just overfitting now.
All right, so this is going into after hours. Notebook plus for after hours. All right, it's coming to you guys in DS12AH. So that comes with the IPYNB plus the pipenv, piplock, or pipfile and pipfile.lock. Cool. So you can check that out and play with it all you want.
Thanks for going a bit later to try and get to the bottom of that. That was helpful.
Yeah, it's just a little tricky. There's a number of factors that are involved that I think might be contributing to the Perceptron not getting a prediction. And honestly, if I was a little bit more awake, I'd play with it some more. But I'm probably going to crash for tonight. We'll figure it out, though. But like I said, if that doesn't work, throw a Keras at it. Pull it up in TensorFlow, which is what the pipenv was for. You don't even need the pipenv if you're not doing TensorFlow. You can try throwing a Keras model at it, right? Hook up some dense layers, try a Perceptron. The basic Perceptron would just be one input, one output layer, right? Set up your input dims to 8 for the stuff. Throw that at it and see if it works better. If it does, then it's definitely some iteration of our weights or our function, activation function, that are the issue, right? I'm thinking it's the weight and the bias. This seems to be heavily favoring 0 just across the board, and like very much so. All of my predicted values are like extremely low, right?
We're mostly 1.
Yeah, it seems to either go to one extreme or the other for some reason. I'm not really sure why. Okay. But yeah, that's all I got for now. Any other questions? Anybody with any lingering things that they don't understand? Cool.
Thank you, Brandon.
Yeah, thank you.
All right. Right on. Well, I hope this has been a help. We'll do this again on Thursday. What do you guys say? Cover some more stuff. All right.
Yes.
Right on. I'll see you all tomorrow.
Yeah.